So I'm going to talk about chemical looping combustion, which is my favorite subject. I'm going to talk about CCS, CO2 capture and storage, and negative emissions, which is another favorite subject of mine, bio-CCS or BECCS. So if we start to the left, we have the principle of chemical looping combustion. A metal oxide is transferred between two reactors and transfers oxygen from air to fuel. And the practice is to use fluidized bed technology for this. And the purpose is to fight the CO2 monster. Now, why do we want to use chemical looping combustion? The oxygen is transferred from air to the fuel by metal oxide particles, as I said. And this means that the combustion products, carbon dioxide and steam or water, which are formed when you oxidize the fuel, comes out in a separate stream. And the steam can easily be removed by condensation. So ideally, by this simple process, you can get pure CO2. And this is because you never mix the fuel and the combustion air. And because you never mix them, you don't need any active, costly gas separation. And this means you can avoid very large costs and energy penalties of gas separation. So this means you have a potential for a real breakthrough in the costs of CO2 capture. An important question is, of course, does this work in practice? Yes. And we have shown it at Chalmers. We were first to show it with gas to the left in 2003. And in 2004 we were able to show it in a very small reactor system, only 25 by 25 millimeters, big reactors. We have then shown it with solid fuels. 2006 we were first also there, and later we have shown it with liquid fuels in the two gaseous pilots we have. And in 2011 we built a bigger unit, 5-meter high reactor unit. And we have total operation of 3,700 hours at Chalmers, which is roughly 40% of the global operational experience of this process. So, and we've examined more than 500 oxygen carriers in laboratory and more than 50 oxygen carriers in actual operation in these units. And we can use cheap materials like iron ore, ilmenite, manganese ore for solid fuels. Now, the options for chemical looping: you can capture CO2 from fossil fuel combustion. Instead of taking carbon from the ground and emitting it to the atmosphere, which is a positive emission, you can remove the CO2 and put it back into the ground, which means you have a CO2 neutral or close to CO2 neutral process. But if you instead use biomass, if you use biomass and burn it, you emit the CO2, you have a carbon neutral process. But if you instead capture the CO2 and put it down to the ground, you have a carbon negative process, which is called BECCS or bio-CCS. So in this way you can do exactly the opposite of what you do when you're burning fossil fuels. So, you have all heard about the Paris Agreement. What does it mean in practice? How much CO2 can we emit? The carbon budget, the decision in the Paris Agreement was well below 2 degrees. So we're somewhere between 1.5 and 2 degrees, I suppose. And the carbon budget for these targets are 200 and 800 gigaton of CO2. And we're emitting about 40 gigaton per year. And this gives us between 6 and 25 years is left of today's emissions. This is a very short time So we will need negative emissions to meet the climate targets. This is an example of a graph. If we do a very rapid, the red one, if we peak very soon and do a very rapid decrease, you can see we will soon get down to negative emissions if you have a linear decrease. So we need to capture a lot of CO2 if we're not able to stop completely by 2045 with this still steep reduction. And Sweden now has a new climate law underway which says we should have zero emissions reached by 2045 and thereafter net negative emissions. So this is important in Sweden. And what is CCS? This is an example of a power plant that captures carbon dioxide, 1 million ton per year. It's in Canada. There were power plants that captured CO2, coal-fired power plants in the 70s, but it was found that it was cheaper to get CO2 from the ground for oil recovery. So they were closed, but this is the first plant that captures CO2 from coal combustion for climate reasons. There is one more operating in the US, and there are also other examples of capture of CO2, and totally about 0.1% of the global CO2 emissions are stored by CCS technology. And this is where solar energy was in a few years ago, 5 years ago or so. So it's behind solar energy, but it's still coming, despite the lack of incentives. And this is a gas platform in the North Sea. It takes natural gas from 4 or 5 kilometers below the sea floor, and it removes CO2 from this natural gas and puts it back into an aquifer which is approximately 1 kilometer below the sea floor. And this aquifer is quite big. It's called the Utsira Formation. The storage started in 1996, so it's more than 20 years with 1 million ton of CO2 per year stored. The area of this formation is 26,000 square kilometers. It's about 200-300 meters high. The porosity is 30 to 40%. If you could use all of this volume, you could store Europe's emissions for 800 years. Now, we're not supposed to emit CO2 for 800 years. And there are a lot of other storage possibilities in Europe and worldwide. Now, Swedish CO2 emissions from biomass, 31 megaton per year. And this can be compared to Sweden's total CO2 emissions, which are 54 megaton per year. So if we captured these biogenic emissions, we could reduce our emissions by more than 150% if we at the same time stop the fossil emissions. And I should say that with respect to 2-degree target, Sweden has already exceeded its fair share of the carbon budget a couple of times. So it's time for us to start the cleanup. But there is also another aspect of this, and now listen carefully because I didn't get this into my slides. Here's a paper that came 4 days ago in Science. It's a roadmap for rapid decarbonization. It explains what we need to do to meet the agreement in Paris. And, I mean, we live in a global market economy. To solve this problem, we need to use the invisible hand, the market. We need a price on CO2. And they say the price we need in 2030, it has to be $50 per ton. And by the middle of the century, it needs to be $400 dollars per ton. Now what does this mean? $400 per ton. It means that these emissions that we already have from large point sources, they are an enormous asset. They are worth more than 100 billions. More than 100 billions. And the cost of capturing them are probably in the range 15 to 30 billions. So this could be a profit for Sweden of 70 to 80 billions every year. So it's like it's more than 2% of the Swedish GDP. So now I have already answered this. The cost is about 0.5 to 1 Swedish crowns per kilogram. And I'll take another example. If the oil companies were forced to capture the CO2 emitted by their petrol, this cost would translate to about 1 or 2 Swedish kronas per liter of petrol. So it's not a very expensive way of doing things. And I just want to say that I do not mean that you should do negative emissions instead of reducing fossil emissions. Both are needed and will be needed. So, thank you.